Welcome to Spaceverse, your portal to cosmic adventures. The James Webb Space Telescope has just made a discovery so startling that it's sending shockwaves through the entire world of cosmology. For years, astronomers and physicists have looked to Webb as the instrument that would peel back the curtain on the universe's earliest moments, confirming the predictions of our models and filling in the missing pieces of the cosmic puzzle. And in many ways, it has. But instead of simply affirming what we thought we knew, Webb is turning the tables. It's revealing evidence that's not just surprising, but deeply unsettling for the foundations of modern science. By now, you're probably familiar with one of its most controversial revelations, the detection of massive, fully formed galaxies in the very early universe. These galaxies appeared so soon after the supposed Big Bang that their existence alone is enough to give cosmologists a massive headache. According to our standard model of cosmology, such galaxies simply shouldn't exist at that time. They're too large, too bright, too structured, like finding a fully grown oak tree just a few months after planting the seed. But what Webb has revealed goes even further than that. The telescope isn't just challenging our theories about how galaxies form and evolve. It's now hinting at something much bigger, something that strikes at the very heart of cosmology itself. The latest observations suggest that one of the cornerstone pieces of evidence for the Big Bang, the cosmic microwave background, or CMB, might not be what we thought it was. For decades, scientists have looked at this faint glow of radiation spread across the universe as a kind of cosmic fossil, the afterglow of creation itself. But the new findings suggest that this light may not be the direct fingerprint of the Big Bang after all. Instead, it could come from something entirely different. Something much closer to home in cosmic terms, and far more complicated than the elegant picture we've relied on for generations. This new research, carried out by Ada Gergo and Pavel Krupa and submitted in May 2025, doesn't just add another wrinkle to the conversation. It opens the door to a bold and unsettling possibility, one that challenges a belief so deeply rooted in modern cosmology that it has almost become untouchable. For decades, the cosmic microwave background, or CMB, has been treated as the ultimate smoking gun of the Big Bang. It's that faint, almost ghostly glow of radiation that fills the entire sky, surrounding us no matter where we look. To scientists, it has always been more than just a glow. It's been a time capsule, a piece of direct evidence, thought to carry the memory of the universe's earliest, hottest, and most chaotic moments. This radiation has been regarded as the oldest light in existence, the very afterglow of the universe's birth nearly 13.8 billion years ago. But according to this new study, that story might not be the whole truth. What if this light isn't exactly what we think it is? What if, instead of being a pristine relic from the Big Bang, at least part of the CMB, or in the most radical interpretation, maybe even all of it, comes from something else entirely? If that's the case, then one of the strongest pillars propping up the Big Bang model suddenly begins to wobble. The radiation we've trusted as a cosmic fingerprint, as proof of a fiery beginning, might not be the universe's birth cry at all. It could be something far more ordinary, and yet, in its implications, far more extraordinary. The researchers focus on a specific kind of galaxy called early-type galaxies. These are massive galaxies that no longer see these galaxies in the relatively nearby universe. But Webb's observations have revealed something astonishing. Some of these galaxies already existed when the universe was incredibly young. We're talking about galaxies forming at redshifts greater than 13. That's just 300 to 400 million years after the supposed Big Bang. According to the standard cosmological model, this shouldn't be possible. Galaxies were thought to grow slowly, merging over billions of years. Yet here we are looking at fully formed, massive galaxies appearing almost suddenly in the early universe. The researchers suggest these galaxies must have formed quickly and in huge numbers, a cosmic burst of creation rather than slow, steady growth. And here's where it gets really interesting. These early galaxies would have been filled with young, hot stars pumping out enormous amounts of radiation. If enough of them were clustered across the cosmos, their combined glow could have filled space with light. Over billions of years, as the universe expanded, that light would stretch and redshift until it looks exactly like the CMB we see today. In other words, the CMB might not be a relic of the Big Bang at all. It could instead be the combined radiation of billions of early galaxies. And the numbers back it up. These galaxies could account for around 1.4% of the total energy in the CMB we measure today. That might sound small, but in cosmology, it's huge. It's enough to affect how we interpret the CMB, and if the contribution from galaxies is even greater, as some estimates suggest, the entire foundation for using the CMB as proof of the Big Bang becomes unstable. If this idea holds, we'd need to rethink almost everything: the age of the universe, how galaxies and structures formed, and even the physics that governed the early cosmos. But this isn't the only discovery challenging the traditional Big Bang model. Webb has also uncovered hints that dark energy in the early universe behaved differently than it does today. Nobel laureate Adam Ree and colleagues found that Webb's data doesn't quite line up with predictions from the standard cosmological model. When scientists measure the expansion of the universe using the CMB, they get one value. But when they measure it directly, using supernovae or nearby galaxies, they get another. This mismatch is called the Hubble tension, and Webb's data suggests dark energy may not be a constant force after all. Instead, it might vary in ways that completely upend our assumptions about cosmic evolution. If dark energy acted differently in different regions of space, then parts of the universe could have expanded at different rates. That would mean not every region shares the same cosmic timeline, making our calculations of the universe's age far less certain. And when we combine that with the possibility that the CMB is contaminated or even misinterpreted, the mystery deepens. Our cosmological models rely on the purity of the CMB signal. If it's mixed with radiation from early galaxies, then the values we calculate for things like the Hubble constant might be significantly off. This could even explain the Hubble tension itself. If the CMB isn't giving us a clean snapshot of the early universe, then of course the numbers don't line up with more direct measurements. All of this points to one conclusion: the universe is far more mysterious than we thought. The James Webb Space Telescope, once expected to confirm and refine our theories, is instead challenging the very foundations of modern cosmology. Perhaps the CMB isn't the afterglow of the Big Bang. Perhaps dark energy isn't constant. Perhaps the universe's story is more complicated and more fascinating than we ever imagined. One thing's for sure: Webb is forcing us to ask bigger, bolder questions about the cosmos. And maybe, just maybe, we're standing at the beginning of a new era in our understanding of the universe. So, what do you think? Could the CMB really be starlight from ancient galaxies, not the echo of the Big Bang? And if that's true, what does it mean for our picture of the universe? Let us know your thoughts in the comments. We'd love to hear from you. Every bit of support helps us create more amazing content. Thanks for watching, and until next time, keep looking up.